Welcome to Part 3, Stack. This part introduces one of the most powerful interview patterns. Stacks are simple, but the problems built on top of them are not. Once you understand the pattern, many medium-level interview questions become easy. Here is the roadmap. We start with stack basics. Then we solve valid parentheses. After that, we move into next greater element. This is where stack thinking changes. Then we explain monotonic stacks. And finally, we solve the stock span problem. Outcome. You will recognize stack patterns instantly instead of guessing approaches. What is a stack? Stack follows one rule. Last in, first out. The last element you push is the first one you pop. A stack supports three core operations: push, pop, and top. All of them run in constant time. In C++, we use the stack container from the STL. It is a container adapter, usually built on top of a DSA. You cannot iterate over a stack. You can only access the top element. This restriction is intentional. It forces correct stack usage. When should you think about a stack? Whenever the problem involves nesting, matching, undo or backtracking, or nearest greater or smaller elements. Stacks are used to remember context, not to store all data, only what matters. Let's start with a classic. Valid parentheses. Given a string of brackets, you must check if they are balanced. Opening brackets must be closed, and they must be closed in the correct order. This is a perfect stack problem. Here is the logic. When you see an opening bracket, push it onto the stack. When you see a closing bracket, check the top of the stack. If it does not match, the string is invalid. At the end, the stack must be empty. Now the C++ solution, we iterate through the string. For every opening bracket, we push it. For every closing bracket, we check if the stack is empty, then compare with the top and pop if it matches. Finally, we return true only if the stack is empty. Common stack mistakes: popping without checking if the stack is empty, forgetting to verify the stack at the end, and using a stack when a simple counter would work. In interviews, stack mistakes usually cause runtime errors, not wrong logic. Now we move to the real power of stacks. Next greater element. This is where stacks stop being obvious and start being clever. Next greater element problem. For each element in an array, find the next element to the right that is greater than it. Brute force compares every pair. That is O of n squared. We can do better. Here is the insight. We do not need all previous elements. We only need elements that could become the next greater element. A stack helps us discard useless values early. We process the array from right to left. For each element, we pop all smaller or equal elements from the stack. The top of the stack, if it exists, is the next greater element. Then we push the current element. Each element is pushed and popped once, so the time complexity is O of n. This is called a monotonic stack. Monotonic means ordered. In next greater element, we maintain a decreasing stack. The stack top is always the nearest greater candidate. Think of a monotonic stack like a filter. Every time a new value arrives, we remove elements that will never be useful again. That is why the algorithm is fast. No wasted work. Now the stock span problem. Given daily stock prices, the span of today is how many consecutive days before today had prices less than or equal to today. This looks complex at first, but it is a monotonic stack problem. We use a decreasing stack of prices with indices. For each day, we pop all previous prices that are smaller or equal. Then the span becomes current index minus the index at the top of the stack. If the stack is empty, the span is the entire range. The C++ solution stores price and index together in the stack. This allows direct span calculation. Again, each element is pushed and popped once. so the solution runs in O of n time. Let's summarize stack patterns. Matching problems use a stack. Next greater or smaller problems use a monotonic stack. Range or span problems use a stack with indices. Pattern recognition is everything. Practice, plan. Solve at least 10 stack problems. Focus on monotonic stack questions. Once this clicks, you will see stacks everywhere. Next playlist, we move to Q and decay patterns.